Now, why did I bother introducing this question by showing you how to use the discriminant for the previous question? Because when you want to work out the restrictions on this locus, okay, the methods we've already been using, they break down. Okay, let's think about the methods for a second by thinking about the two kinds of locus that we've been interacting with already. So when you've got a red marker, when you've got a red marker, there's a marker. Okay, when you take any parabola, right, and you've got some chords on it, okay, we've already sort of said it's self-evident that the midpoints of those chords must be within the parabola. Okay, and likewise, or actually conversely, because it's the opposite, if you're getting intersections of tangents, we've said wherever they are, they've got to intersect outside the parabola. Yeah? Okay. But there's a problem with our question, this one. Okay, I want you to draw for yourself 3 sets of parabolas on your page next to each other in a row. If you've got a template, bonus points. Draw up 3 parabolas and let's illustrate something.
Is this still under the same?
It's still the same question. Now, just to save you some time, unless you've already done it, just draw the parabolas. Don't even worry about the x and y axes. Okay, I'm just interested in the shape. Okay, and we're going to draw some normals on these in a second, right? So draw 3 parabolas next to each other. Okay. Now let's think about this. Remember what a normal is? It's just perpendicular to the tangent. It's the line perpendicular to the tangent at a particular point. Now where's it going to lie? Well, in this middle parabola that you've drawn, right? Let's put this case in. What this particular question has told us is, for certain kinds of normals, right? Their point of intersection, where they collide, is going to be back on the original parabola. Okay? So use your ruler, try and do this as neatly as possible. But pick a couple of points, like these ones, okay? And maybe get them in different colors if you've got them, okay? Do it on this middle one. And if you draw it right, the intersection of the normals, like say these two, let's draw this one, that's not straight at all, and this one, okay? So pop in like a little right angle here just to illustrate what they are, okay? The intersection of these normals is right on the parabola that you started. Okay. However, it's not that hard to think of cases where this doesn't happen, that they don't intersect on the parabola. Can anyone draw for me? How can we make normals that don't intersect on the parabola but inside the parabola? Okay, so if you've got 2 normals, let's just leave that one in place. Sorry, I should have held on to this. Let's put that one still there. Okay, so that's a normal. But if you take the normal from the opposite direction, right, you flip it over, quite clearly, the normals intersect within the parabola. Okay? That's true, but I'm thinking about, we're trying to make geometric arguments that apply to all kinds of normals, right? You're right that it doesn't make sense in this case, but you'll see why it's important in a minute. So they can intersect inside, they can intersect on the parabola. Could they possibly intersect outside the parabola? Answer, yeah. What kind of condition would we need for them to intersect outside? Yeah, sort of close together, but not too close together, right? Because if they're too close together, they'll still intersect inside. Right? But if they're close together the right amount, and you've got, depending on what kind of focal length you have and so on, okay, they're going to do something like this. You'll have one that chops through like that, and you'll have your right angle. And then the other one is going to, now I'm not sure if I've drawn this well enough, but we'll just approximate. No, that's pretty right angle-ish, isn't it? So that's convincing enough, right? So have a look at this, okay? Intersection of normals. if you want to put like a little subheading over these three diagrams, okay, it can happen within, or on, or outside the parabola. It can go anywhere you'd like, right? So we can't make the same kind of geometric argument that we could with midpoints, which are inside, or intersection tangents, which are outside. You just, you can't do it, okay? So that leaves us with the discriminant. That's the only way we can do this, okay? So how shall we find the restriction?
Wait, so with normals, whenever it's intersection of normals, you just have to discuss.
Yeah, that's right. This is the special case that I was talking about before. Remember I said you've got to have these two methods. You can prefer one, that's fine, but you've got to know how to do both. This is why, okay? Right, let's find the restriction. I'm going to go with this equation here.
So in general, for everything else, generally you can put
I think it's faster. Yeah. And it's less mental gymnastics, to be honest. Right, now this is the equation we had. I think this was the final equation we had for x. Yes? Okay. So what do I want to get this into a form that I can use the discriminant on? What do I have to get rid of? I've got to get rid of a parameter, okay? So in order to do that, I've rubbed it off already. I'm going to use the fact that PQ is equal to 2, right? So if I wanted to get rid of Q, I guess I'd say Q is equal to 2 on P, right? So, oops. Okay. So, what can I go through here? Let me just expand it first. 2P minus 4 on P, and there's my X. You can start to see the pattern, right? You often get this fraction business, so I've got to multiply through by P, and that's what makes the quadratic. Okay, so I have Px 2 P squared minus 4. Okay, yes. So let's put it all on one side. Px plus 4. Okay, for real solutions of P. Okay. The discriminant is greater than or equal to 0. Okay, so b squared is x squared minus 4ac, that's greater than or equal to 0. Okay, so x squared, 4, 8, 32. So it's not quite as neat. Okay, but well, what's the square root of 32? What's that work out to? 4 root 2. Yeah? So when you're taking this parabola, you're going to be less than the negative value or greater than the positive value. Or like I said before, you can be fancy, you can use absolute value to express that all in one go. Okay? But that's it. Okay? So just to review, we went through it the same way, but to find the restriction, because the intersection of the normals is a special case, okay? Geometric arguments, it's not that they don't work. You can actually use them, but it's just far too complicated. You can't just say it fits one of these cases, okay? It has to do with the fact that this point, 0 minus 2, that we've chosen, right? That's terrible. 0 minus 2. If you think about the kinds of chords you can form that pass through here, okay? You know, for example, you could form, this needs to go steep. You could form this chord, right? Or you could form this chord, or you could form this chord, but at a certain point you can't form chords anymore, right? Because, you know, the lines that you draw through, they're just going to go whoosh, and they'll never reconnect, okay? So what you've got is actually just cutting through, and there are no 2 points that I can use to say, well, here's normal number 1, and here's normal number 2, okay? So this restriction, saying it has to be far out this way and far out that way, it's actually blocking out this part in the middle where you just can't make normals that go through that point, which is what you were mentioning before. You can't do these kinds of normals, okay? So there is a geometric argument, but it's so convoluted, you might as well just use the discriminant method, because it makes sense. You can stand by the algebra and say, I see why it works, okay? Did you have a question?
Yeah, is the discriminant usually greater than 0? Like,
it has to be,
yeah.
yes. Because what we want, right, is for P to exist. We want it to work. We don't want it to be some kind of imaginary floating off thing.
So it's always greater than 0, right?
For these kinds of questions, yeah, because what we want is real solutions. And the condition for real solutions is the discriminant being greater than 0.
Don't you always want real solutions then?
No, I mean, if the question was one of those contrived ones where it's like, here's a quadratic, you know, kx plus 3, and they say, find the values of k that make the roots not real, right? So you would need the discriminant being 0, and then you solve that for k, right? But in this case, we always want real solutions. Question?
Oh yeah, is there any other like common case for this?
This is the common case. And to say that this is the common case is a bit of a misnomer because it's not common at all. This hardly ever comes up, but I wanted to show it to you and have it on record so that you can be like, well, I know, this is the weirdo one, this is where it comes up. If it comes up, I'll be ready for it.